Hello, in a previous video I explained the basics and assumptions to design a reinforced concrete beam under bending moment. In this video we start with calculating the factor resisting moment for an existing concrete beam. So you can assume that there is an existing building, and through the surveying we found out that the width of this beam is 400 and the depth is 500, and by using the ultrasound devices with non-destructive tests we found out that this beam has two bars number 25, and by using the Schmidt hammer we found out that the concrete strength is 25 MPa and the F yield of the steel is 400 MPa. Based on what we assumed in the other videos, we have the following assumptions. The force in the steel, Ft, equals to the force in the concrete, Cr. So the Cr, the force in the concrete, can equal to Fs to provide internal equilibrium. And the other thing is we can use the stress block, which will have the stresses of the concrete will be in a rectangular shape, and I can have the stress equal to alpha 1 times phi c times F prime c. Now, based on the location of the building, we can have the outside cover, which is the distance from the external of the beam to the stirrups, to the outside of the stirrups. Normally there is a stirrups inside the beam, and inside the stirrups we have the steel bars. Now the cover between the outside of the concrete to the stirrups will be assumed to be 30 millimeter, as an internal beam is not exposed to the outside, and then assume that the stirrups diameter is 30 millimeter and the distance from the stirrups, the inside of the stirrups to the center of the bar, will be 25/2. Now the depth of the beam will be equal to the distance from the top side of the beam to the level of the center of the steel bars, and this depth equal to 500 minus 30 millimeter the concrete cover minus 10 millimeter is the stirrups minus half of the diameter of the reinforced bars, so 25/2. Now I have a distance here from this level to the outside of the beam equal to 450 millimeter. Based on our assumptions and the equation what we explained in another video, the tensile force in the steel bars, which is here as a Tr, equal to phi s times Fy times As. Phi s is the material resistance factor, which is a factor to reduce the strength of the steel, which is equal to 0.85, times Fy, which is 400, and area steel, the existing area steel in this beam is 1000 millimeter square. Now when we calculate this Tr, we know that Tr will equal to Cr, and Cr is this value here, that's equal to alpha 1 times phi c times F prime c. We know these parameters, times A times B. A is the depth of the compressive zone here, and B is the width of the beam. So I know B in this beam, which is 400 millimeter. Now when we calculate the Tr and make that Tr equal to Cr to provide internal equilibrium, then we can calculate A. When we calculate A, now we can estimate the location of the Cr within the cross section, because the Cr will act at a distance from the outside face of the column equals to A half. Now calculating the steel force Tr will equal to Tr equal to 0.85, that's phi s, times 1000, that's area steel, times 400, that's the Fy. That can bring us to 340 kilonewton. based on our assumptions that the CR will equal to TR, which will be 340 kilonewton. Now CR equal to 0.8, which is alpha 1, and we have equation in another video showing that, and alpha 1.8 times phi C 0.65 times 25, which is the F prime C, times 400 is the width of the beam, times A, that's the depth of the compressive zone. Now A from this equation will equal to 65 millimeter. Now the internal resisting moment MR will equal to this force, which is T, times this distance, and the distance between CR and TR here will equal to the depth, which is 450, minus a half. So I can have this distance. So the 340 kilonewton times 450 is the depth, minus a half, 65 over 2, and we divide that by 1000 for the units to have it in meters. So at the end we have the resisting moment 142 kilonewton meter. So that's the resisting moment on the beam. Now if we have any load on the beam, we can calculate the moment of this load, and then we can compare the acting moment with the resisting moment, and we can say, okay, this beam can take this moment, or this beam needs an external reinforcement. And one way of adding external reinforcement is adding FRB as outside, or there are different ways to increase the bending capacity of this moment, of this beam. Sorry. Now, when we calculate the beam under flexure, we have two ways of calculation. So one is to calculate the capacity of an existing beam, and that's what I have done already. So if you have an existing beam, you can calculate the internal capacity of this beam to resist bending moment. The other way is to design beam from scratch. That will be for a new building. And how to design beam from scratch? So we have to estimate the beam depth, and estimating the beam depth will be based on few items. Number one is based on the Canadian code A23.304. We have the depth of the beam can be L, the clear span of the beam, divided by 16, or L over 18 if it's one end continuous. That's if it's simply supported, I can estimate the depth of the beam by 16 divided by 16. For example, if you have a 4 meter D span, then you divide the 4 meter by 16, then you can get the depth of the beam. That's an estimation at the beginning of the design. If you have both ends continuous, then you can have Ln divided by 21, or if you have a cantilever part, then you can have the cantilever part divided by 8, then you can estimate the depth of the beam. If you are using this table, which is table 9.2 in the Canadian code, then you don't need to calculate the deflection of the beam. If you don't follow this ratio, then the deflection of the beam should be calculated. That's number one. Number two, for the estimation of the beam depth, we have to look at the architectural drawing to see what is the depth and the clear height available on the drawing, and then we can finalize the depth of the beam. So the depth of the beam should be calculated. And choosing the material, we know that the material Fy for the steel will be 400, but the class of the concrete can be chosen to give us the optimal design. We can have F prime C from 30, 35, 40, and so on for the beam. Then we have to calculate the straining action, the bending moment, and the shear force. Bending moment and the shear force. Calculating the area of the steel to resist the bending moment, that has to be done. So we have to add reinforcement to resist the bending moment, and then we can start calculating the stirrups to resist the shear force. We have to add stirrups to provide shear resistance for the beam, and there are minimum requirement for the stirrups. And then we have to calculate the beam deflection if we don't follow this equation. So design the beam from the scratch will include the following one more time: estimating the beam depth and also the width, choosing the material, what's the F prime C I'm going to choose, calculating the external straining action, the bending moment and the shear force acting on the beam, and we have to add the beam own weight to the existing forces, and then we have to calculate the steel area to resist the bending moment, and then we have to calculate the stirrups to resist the shear force, and then we can calculate the beam deflection. Now there are different requirements in the code, which is the minimum desired requirement for beams. The first one is the minimum area of steel is 0.002 times the area steel. What does it mean? It means that I have to add steel reinforcement, for example, in this area, and to resist the bending moment. But this steel area should not be smaller than 0.2% of the area of the cross-sectional area. We have to calculate the cross-sectional area, and then we take 0.2%, like 2 divided by 1000 times this area, and that it should be less than the area what we add to our beam. That's number one. Number two is the minimum number of bars. I have to add to have at the bottom at least 2 bars, and at the top other 2 bars for as a minimum for that beam. Now if my beam depth from the top here to the bottom is more than 750 millimeter, then we have to add skin reinforcement. What are the skin reinforcement? Are bars on the side of the beams, and that has to be added to minimize the crack widths on the side. Otherwise we can have cracks on the side of the beam. That we call it skin reinforcement. And let's see here, it is preferred to have or to choose smaller bar sizes and increase the total number of bars rather than getting bigger sizes and less number. What does it mean? Here in this beam we put 6 bars with a smaller diameter. Now we can choose maybe only 3 big bars, and these big bars here will lead to creating cracks in the beam. So it is preferred to choose a smaller diameter or smaller bars and increase the number of bars than having less number and big bars, because that will lead to having bigger crack width. The other thing is the maximum spacing between the steel bars is 500 millimeter or 3 times the depth of the beam. So the spacing between these two bars should be bigger than 500, less than 500, or less than 3 times the beam depth. That's very important. The other thing which I would like to mention is the spacing between these bars should be bigger than 1.5 the aggregate size. So if you are using aggregate size of 20 millimeter or 25 millimeter, you multiply the aggregate size by 1.5, and then you have this spacing between the bars to be more than that. That will enable us to have the concrete, or to pour the concrete inside the formwork and get the vibrator and make sure that we can have a tight or compacted cross section. With this information here, that concludes this video, and thank you very much.